Hello, in this video we will show how to train a perceptron model for classification in Python. So we know machine learning is the basics of artificial intelligence, right? And there are different kinds of machine learning model using neural network. And the perceptron is actually a single neuron estimation method, or the training method algorithm. So if we can understand the perceptron well, then it's very easier to understand the larger neural networks. So what is a perceptron algorithm? It is actually a simple method to estimate a binary classification model with 0 and 1. And we define a decision function, sigma z. This function is called activation function in a machine learning neural network. So we get the features or the variables of the data, and we set an item called z. Z is the multiplication of weight, the parameter, with its feature. Then we take it together and plus b, the bs item. So w times x, this is the matrix multiplication plus b. This item is called z because this is a linear item, right? And usually we will use a non-linear activation function sigma z. And in the perceptron algorithm, we use the very simple sigma z. This is called unit activation function. So in perceptron method, we will make sigma z equals 1 if say this is net input. This is net input, say, right? And if this net input larger than 0, we will classify, or we will make the y, the estimation of this class is 1. So if 0 is less than 0, if say not larger than is less than 0, then we will classify this observation is 0. So this figure shows the activation function in perceptron. Now this is the net input, and in this line the result is 1. And in this part of the line, the result is 0. And so this is the non-linear function. And in the more complicated neural networks, and we will use other kinds of activation function. But the basic idea is the same. From a net input, usually this is a linear part of the multiplication and plus a bs item. Then we make a non-linear activation function based on the different sigma function, right? So this is the basic idea of the perceptron. And after we have defined this model, then we want to estimate the weights and the bs. So only we estimate the value of bs and weights, then we can make projection later, right? So how to estimate? So this is called the learning rule. We use numeric calculations, update the weights and the bs, and we set initial value with weights and bs, then we update it. So the main procedure is initialize the weights and bs to 0 or small random number. Then for each training example, xi, we will compute output value y based on the perceptron formula we have shown in the previous page. Then from this predicted value, we will calculate the difference between observed value and the estimated value. Then this part will times this x value. So here I means the ith observation, and j, if we have j means j's weights or the j's variable, right? So here is for how many features in the model in the observations. Then we will use the same number of weights, right? Then plus a BS. So J is the weights index and I is the observations index. So for example, we have 1,000 observations. So here I is from 1 to 1,000. So for each weight, we will use the difference between observed observations and estimate the observations for each observation. Then we will update with a small learning rate. This is a very small number, eta learning rate, and times this corresponding feature value. And for the BS, we just use this difference part and times this learning rate. So this learning rate will update until for each epoch, we will update for each observation. So here, each observation update one time, and within each epoch. So each epoch, maybe we can define 100 epoch. But sometimes if the learning rule can be converged within, for example, 500 epoch, then it is okay. But sometimes from the non-linear case, we will not get the converged results for the parameter, for the weights and the BS. So we will define a limited time for the epoch. So this is the learning procedure for the weight and BS in the perception model. So this figure shows clear procedures of perception algorithm. So we get the data and we define BS and weights. Then these two parts multiplied together and plus BS. Then this is net input. Net input, we use a sigma represents the net input. Then this is a non-linear, and here is the unit function for activation or the decision rule. Then based on this decision rule, upon this net input, we will get output value of y, 0 or 1. Then use this information, and with the observed y, we will get error. So from this error, we will update the weights and BS. So this will run for each observations and for multiple epoch until either we get the converged value or either we get not converged value but to the limit of epochs we defined. So next we show example in Python for the perception. So we will use a class, set a class for the perception because we have several function method we will use. So in the description of this class, eta is a floating learning rate between 0 and 1, and n item is the integer value for the training for the passes or epoch. And we also set a random state because we use a random number generator for this. This is a seed for random number generator. And for this class, there are several attributes. This W is the weights, and BS for the B for the BS, and their errors. Errors is for each learning epoch. We will use error summing together upon from each observation. Then we define initial for this class, self, eta, and epoch and a random state with initial values. Those three attributes which are defined when this class object instance is created. Then we define define method called fit. So fit is the training training procedure. This is also same as what we will update the value of the weight and the PS. So there are several parameters. X is the feature, the shape with n examples and n features. So for example, there are 1000 observations and four variables. So this is an array of 1000 rows and 4 columns. And Y is a shape with n examples. So 1000 observations will have 1000 Y value, right? Also array-like. So they're both from NumPy array, and will return in this method will return object, because this object self contains all the information. So we create an object called RGN, random number generator, using the random state from this function. Then we will set the initial value for weights and PS. Initial value weights is coming from normal distribution with the location 0 and scale standard deviation 0.01, and the size is X shape 1. Shape 1 is the same as the number of how many variables, because shape 0 is how many observations, right? Shape 1 is the second axis is the it has the number of how many features, and the PS is a floating number with 0. Then we will define an empty list for the errors. So here list errors, we will append the error, total error for each epoch, because error will comes from each observation and sum together within each epoch. So for each epoch we'll have an error. For each epoch we'll have an error. So for example, we defined 50 epoch, right? So the result for the errors, a list will have 50 values. Then a loop, the training loop. We do not use this training index number, so we just use underscore here in the range for this n iteration. So first we will set errors to 0, and we will zip X and Y. So X is a 2-dimensional array and Y is a 1-dimensional array. So we zip together, then take X and a target. For each X and Y value, we will update. We will use update. So the update actually is the small number of eta times the observed Y value minus the predicted Y value. So here is a method predicted. We will see the definition later. So here we just know the difference of observed and estimated or the predicted value difference, then times eta. So we set this part called update. And for the weight parameter, it will be the update times x1. We see. So for the weight, this is update. This part is update. Eta times yi minus y hat. Then for the weight, we will times xj. And for the BS, we just use the update. Then we will record these errors, because here is each of observations. So we will sum together all errors. If these two parts is different, we call the error, right? If this is the same, no error. So we just use this part is not 0, then sum together. So this is the errors for each epoch. Each epoch includes all the errors from observations, estimation, and compared with their observed y value. So we will check, for example, here 1000 observations, and for each observed value, each observation, we will check if the predicted value is same as target value. If they are not, for example, 1000 observations, maybe we get a 300 predicted wrong. Then we take this error. But for the 700 predicted right, we do not use this information to update because they are right. They are right. So we only use the wrong information called error. Then we update based on this error. Here. So this is the key of the learning rule. Then for each epoch, we will append their sums of error in this error list. So return self for this fit method. So this fit is for the training. Fit method is for the training. Then the next method called the net input. It is very simple. We just calculate net input, which is the multiplication of x features and their corresponding weights value, then plus a BS part. Then the predict function using the net input, and because this is the unit in the perception learning rule, it is the unit function. So this net input, if larger than or equal to 0, then we will get the result 1. If not, then we get the result 0. So this is the activation function, or called predict method. Here we use a predict. So the three function in this class is fit, and fit for the training, and for the net input, and predict. In the fit, we use predict results, and in the predict, we will use net input. So this is the backbone of this algorithm. And here we can just bypass this really not useful. So next we will use the data, because we have not got the data yet. We will use the Iris dataset. Iris dataset for the machine learning. It's actually for about 150 observations and a class label for 3 kinds of plants. And actually we will use 2 classes from this dataset, and there are 4 features, and we will use 2 of them. So we downloaded this data first into our working session. It is successful. Then this data frame, we will show the last observations, 5 observations. You can 0, 1, 2, 3, 4. So the last feature is used for the class label, and the first 4 feature are numerical. Actually, this is for the sepal length, sepal width, and the petal length and petal width for each plant. Then we will use the data for first 100, because we will use only 2 classes, so we will not use the last 50. The first 100 observations including 2 classes, and we use the last feature. Then using ilook function of the pandas package, then get this information out, then use the values. So it will be a NumPy array-like values. Then we set this to y, because we will use this for the labels. Then we change this y, because this y information is like a character. Then we will change these values to 0 or 1. So if you can see, the y now is 0, 0, 1, 1, 1, like this. And for the x, we will take out 2 features and also use the first 100 observations. Then use the value attribute to transform to the NumPy-like data. So x, y are both okay. Then we will show sketch of x and y. Then we set the colors for different observations with different classes. So this is the 2 classes with x and y, with the 2 features x1 and x2. They are corresponding scatter plot and color represent different classes. So you can see here, actually there can be correctly classified with a linear line, right? And actually this linear line will be like the regression line between x1 and x2. So next we can train the module. First, we will set an instance of the perception class we defined. Oh, sorry. We have not learned this. First, learn these classes. Then we will create an instance of perception. Then we can just use the fit method to train the module. It's very quick. Then we show, because of the trained and errors list will have errors, so we show errors, and actually there are about 6 epoch it is converged. So the error is 0. 1, 2, 3, 4, 5, 6. Only 6 epoch it went. It has been trained, finished. So next we will define a function called plot decision region. So in the decision region function, we first will make some lists for the colors and C maps. So colors actually for we can use at most 5 different classes, but here we use only 2. Actually, only use 2 of them. And we will use the minimum of x and the maximum of x2 features. We will define the map we will plot. So use the mesh grid function to get 2 matrices based on the values by column and by rows for each variable's information. Because we will plot a pair of x1 and x2. And for each x1 and each x2, we will define very small points in the range, maybe 1,000, several thousand. So there you look like the map with the same color, because it's a very, very dense. So then use the label. Then use the control function to plot the labels for each point scatter plot. So next, we will use the plot for the real numbers. So the first part is plots a very dense point with different colors, with different colors inside this map. And for each map will be, for each point within this map, between X and Y, thousands, millions of points, we will predict their values, and based on this predicted value, we will set colors. So this uses the control F function. And for the second part of this function, we will plot the real scatter plot from our observations and with different colors for the different classes. So we will show how it will look like. Then we just use plot region, decision region, and we set the legends. So you can see these two area for the color is based on the module, blue area, red area, and we set millions of points in this map. And for the different map, we will we make prediction, and with the prediction for the class 1 and class 2, and with different colors. And these points are real observed points from our observations, and also with different colors for different class. So you can see the map. This is actually, this line is a decision rule. This decision rule is actually 100% correctly classified with our observed points, right? Because no observed points on the other side, on the wrong side of this decision line. So this video we just showed the very basics of the machine learning with neural network, and actually this is a simple neuron called perception algorithm or perception learning rule. So understanding perception learning rule is quite important for the further learning for the neural network. And focus on our videos, our channels, and we will make more videos for machine learning with Python later. Thanks for watching.